morning, dear students. In the last class, we derived the expression for strain energy of the beam. The expression for strain energy of the beam is 1 by 2 into integral of EI into d square V by dx square whole square into dx over the length of the beam. And this is the expression for strain energy of the beam. Okay. We know that the potential energy pi of an elastic solid equals to the strain energy plus work potential. Okay. Work potential is due to the work done by the external forces. What are the external forces here? The external forces are the distributed force, the concentrated force, and the couple. We have considered distributed force, concentrated force, and couple on the beam. Right? Therefore, I take the distributed force P and determine the work done by the distributed force. Okay. We have considered an element of length dx. We have considered, observe carefully, if this is the beam, we have taken a beam of this type, okay, with one end hinged and other end is supported on rollers like this. Okay. Now here, this is the distributed force acting vertically upwards like this. What is the load intensity P? We have considered an element of thickness dx, distant x from the first end. Okay? So therefore, if you isolate this element and draw separately, this is the element of thickness dx. What is the force? What is the force acting on this element? It is simply P into dx. It is the force. It is the force acting on the element. Therefore, P dx into, what is the beam deflection at the same section V? Therefore, I get PV dx. So, PV dx gives me the work done by the force acting on an element of length dx. But I want the work done by, the distributed force acting over this length. Therefore, I have to integrate this. Understand? Not over the entire length of the beam, remember. Not over the entire length of the beam. Here the distributed force is acting over only this much length. This I say LP. Therefore I write here LP. It is not acting over the entire length of the beam. If it is acting over the entire length of the beam, I take entire length into consideration. Next. What is PM? PM is the concentrated force acting at point M. Like this. This is the concentrated force acting at point. Right? And what is the VM deflection at this point M? I say VM. Therefore, PM into VM. That is the work done by the concentrated force PM. If there are several concentrated forces, then how you write? Say M equal to 1, then I get P1, V1. Then M equal to 2, I say P2, V2. So when you sum up like this, for a set of concentrated forces acting at different points, then you write the sum of PM into VM like this. As M varies from, say, 1 to N. As M varies from, say, 1 to N. Therefore, we express like this, the sum of PM into V. And coming to the couple acting at point K, this is point K, and couple is acting anti-clockwise direction, MK. Okay, therefore, here what is the tendency of this couple? The tendency of this couple is to rotate the beam section by certain angle. Understand? Therefore, this section, tends to rotate in the direction of the couple. Hence, the work done by this couple MK equals to MK into Vk dash. Vk dash represents the slope. Right? If there are several couples acting at different points, then determine the work done by each couple. Then sum up. Therefore, I write here the sum of Mk Vk dash, as k varies from say 1 to n. If there are n number of couples acting at different points, then we write M1 V1 dash plus M2 V2 dash plus M3 V3 dash and so on. Okay. Understand carefully here. We have minus. We have minus. Why? Because as I told you several times, work done by the external forces is negative. Hence I put minus. So what is this expression? This is the expression for determining the potential energy of an elastic beam of length capital L. Okay? Now, this term, what this represents? This represents the strain energy of the elastic beam, the strain energy of the entire beam. This results in global stiffness matrix. Right? And these terms, they result in different matrices. Okay? That also we know. The symbols that I have used are, explained here. Go through. Pk is the point load at point M, and Mk is the couple applied at point K, Vm is the beam deflection at point M, Vk dash is the slope at point K, and P is the distributed load per unit. Now we shall see the finite element formulation. This is very, very important. Okay. Because we are discussing about the one-dimensional beams, we use one-dimensional beam elements. One-dimensional beam elements. See here. This is a one-dimensional beam element. The element has uniform cross-section. The element has uniform cross-section. Okay. Element number is denoted by E, which is encircled like this. Okay. Now, for an element E, the first node is denoted by E and second node is denoted by E plus 1. The first node is denoted by E and the second node is denoted by E plus 1. When E equals to 1, the first node is 1 and the second node is 2. Okay. Right. The one-dimensional beam element has uniform cross-section. It is, remember, a two-noded beam element. Okay. Here, each node has 2 degrees of freedom. Each node has 2 degrees of freedom. What they represent? Beam deflection and slope or rotation. Therefore, at each node, we have a deflection and a rotation or slope. Okay. You can also represent like this conventionally. Draw a line with 2 end points. They represent nodes 1 and 2 for element 1. Node 1 has the translation which represents the beam deflection Q1 and a rotation or the slope Q2 like this. Next, node 2 has the beam deflection Q3 and rotation Q4. Understand? To represent, okay, the degrees of freedom, what convention I follow? If J denotes a node, okay, now the beam deflection at the node J is denoted by Q2J minus 1 and slope Q2J. This convention I follow. When J equals to 1, that is for first node. Now, Q2J minus 1, Q1 you get like this, and Q2J, Q2 you get like this. When J equals to 2, that is second node, then what you get? Q2 into 2 minus 1. Q3 you get like this, then Q4 you get like this. This convention I follow. to denote both degrees of freedom. What they represent? Beam, deflection and slope or rotation. Understand? Right? Now, if you have an elastic beam, that you have to discretize into several beam elements. This is the beam element. Beam element. How you call it? It is a two-noded beam element with each node 2 degrees of freedom. Okay? Right. Now, when you have a beam, you have to discretize it into several beam elements. Okay? Now, this I say a beam of uniform cross section. Okay? It is prismatic in shape. Now, here the beam is divided like this into several elements. This is first element from here to here, second element from here to here, third element, fourth element. This is first node, second node, third node, fourth node, fifth node. Okay. Here the entire beam represents a domain. Therefore, in the domain, all degrees of freedom at the nodes are represented using capital letter Q. That is what I told you in the previous class. Therefore, here Q1 represents the beam deflection at node 1 and Q2 represents the slope. Similarly, Q3 represents the beam deflection at node 2 and Q4 represents the slope. Each node has 2 degrees of freedom. This is how you can. All element numbers are encircled, as I said. Okay? Now, if you observe, the differential equation for beam deflection. What is the differential equation? D square V by dx square equals to m by EI. What V represents the beam deflection. If V is the beam deflection, and what is the slope? The first derivative of dV by dx. I say dV by dx equals to V dash. Hence, at each node you can also represent like this. At first node, I represent the beam deflection by V1 and the slope by V1 dash. This convention also we can use. And at second node, the beam deflection is denoted by V2 and the slope by V2 dash. Remember, right? Once you discretize the domain into subdomains, you have to give the element node connectivity information. Right? This is the table giving the element number and the local node numbers. For element 1, right? What is the first node? 1. What is the second node? 2. This is first node, this is second. For element 2, I say node 2 is first node and node 3 is second. For element 3, I say node 3 is first node, node 4 is second node. For element 4, node 4 is first node, node 5 is second. This is how I can prepare element connectivity table. Okay, next. Now, element displacement vector. I use a small q to denote the element displacement vector because we have a one-dimensional beam element here with 2 degrees of freedom at each node. With 2 degrees of freedom at each node. What are they? Q1, Q2, Q3 and Q4. Okay. Therefore, you can represent these 4 degrees of freedom, right, as a column matrix. Hence, the element displacement vector is a column matrix having the elements Q1, Q2, Q3 and Q4. How do you write transpose of a row matrix? That is what I have done here. Okay. Now, in the previous slide, I told you V represents the beam deflection. Therefore, instead of Q1 you can write V1. And instead of Q2 you can write V1 dash. Both are same. That is the reason why the element displacement vector you can also represent like this. Okay. Element displacement vector you can also represent like this. In place of Q1 you can write V1. In place of Q2 you can write V1 dash. What is Q2? It is slope at node 2. The slope at node 2, how you determine? It is simply the first derivative of the beam deflection, that is dy by dx. Okay? At node 1, remember, at node 1. Therefore, I say this is V1 dash. Now we get this dv by dx at x equal to x1. You get V1 dash. Next, Q3 equals to V2. And Q4, how you get, Q4 is simply V2 dash. How you get V2 dash equals to dv by dx at x equal to x2, remember. In this case, x equal to x1, at x equal to x1. That no. Right? Therefore, Q you can also represent like this. And what capital Q denotes? It denotes the global displacement vector. I told you, the global displacement vector represents the nodal displacements in the domain. What are they? Q1, Q2, Q3, Q4, Q5 and so on and so forth. Hence it's a QN. We also define this as a column matrix. Right? Hence I have written here the transpose of the row matrix. Okay. So now, shape functions, very, very important. We know that, shape function is an interpolating function. Understand? It is a function that interpolates the nodal field variables with the unknown field variable. Now, for beams, we derive the Hermite shape functions. We use the Hermite shape functions. Okay. Now, Hermite shape functions are the polynomials. We use polynomials as the shape functions. We use polynomials as the shape functions. Now, how you choose the polynomial? That is the question. If you observe the one-dimensional beam element, two-noded beam element, each node has 2 degrees of freedom. This is Q1, this is Q2. This is Q3 and this is Q4. Understand? Therefore, how many non-nodal field variables are there in the element? 4. Hence, you can choose 4 generalized coordinates in the polynomial for the beam deflection. Hence, I can write the beam deflection V, right, as say A plus B J plus C J square plus B J cube. This is how I can define the beam deflection in the natural coordinate J. You can also derive the shape functions in the Cartesian coordinate X. Cartesian coordinate X. Okay? Here in one-dimensional beams, we take, the global reference frame with the Cartesian coordinates X and Y. Understand? X and Y. Because it is a one-dimensional domain, we specify each point with only one coordinate X. Hence, the beam deflection is dependent on the variable X. V is a function of X, therefore. V is a function of X, therefore. You can also derive the shape functions assuming the displacement, that is the beam deflection, as say A plus bx plus cx square plus dx cube. Then you get the shape functions in terms of x. Okay. For each element, you can use the local reference frame with the natural coordinate j. Therefore, I derive the Hermite shape functions for a one-dimensional beam element using the natural coordinate j. That is the reason why I choose the beam deflection like this. I have written here V equals to A plus Bj plus Cj square plus Dj cube to derive the Hermite shape functions for one-dimensional beam element. Okay, then determine V dash. What is V dash here? dV by dj. Why you have determined V dash? Because at each node there exists 2 degrees of freedom. Beam deflection and slope V dash. Therefore V dash equals to, if you differentiate this, B plus 2Cj plus 3D j square you get. Understand? In this polynomial there are 4 unknown coefficients which you have determined first. Therefore you want 4 conditions. What are the conditions at node 1? Firstly, right? J equals to minus 1. We know that if you take a beam element like this with 2 nodes 1 and 2, at node 1 J equals to minus 1 and at node 2 J equals to plus 1. And the length of this element is varying as J is varying from minus 1 to plus 1. The length of this beam element is varying. The length of this beam element is varying as J is varying from minus 1 to plus 1. Right? Now, that is the reason why I take node 1. At node 1, J equals to minus 1. Right? J equals to minus 1 and V equals to V1. Therefore, so we get V1 equals to, put J equal to minus 1. A minus B plus C plus D, you get like this. When you put J equal to minus 1. And at same node, you can also determine the slope, that is V dash, at J equal to minus 1. That is next condition. At node 1, J equals to minus 1 and V equals to V dash. Sorry, V dash equals to V1 dash. Okay, therefore, V1 dash equals to, in this expression put J equal to minus 1, you get V minus 2C plus 3D. Second condition. Next, third condition. Take node 2. At node 2, J equal to plus 1 and V equals to V2. Okay, then V2 equals to A plus B plus C plus D. Next, fourth condition. At node 2, J equals to 1 and V dash equals to V2 dash. We have the expression for V dash. Put J equal to plus 1. Then V2 dash equals to B plus 2C plus 3D. We have 4 unknown coefficients and we have 4 relations, 4 expressions. Okay. Now solve them. If you solve them carefully, you get the values of A, B, C and D like this. This is the expression for A. This is for B. This is for C. And this is for D. Okay. Now, the values of A, B, C and D, if you substitute in the expression of beam deflection, here in this if you substitute, then you get an expression like this, a lengthy expression. Be careful. In terms of J, you get an expression like this. Okay. Now if you put J equal to minus 1, then what do you get? You get the beam deflection at node 1. This is node 1, this is node 2. If you put J equal to minus 1 in this expression, okay, in this expression, if you put J equal to minus 1 in this expression, right, you get deflection at no, because this is the expression for V. Here, this expression contains V1 dash and V2 dash. What is V1 dash? It is the slope of the beam at node 1. It is the slope of the beam element at node 1. What is V2 dash? It is the slope of the beam element at node 2. Remember. Okay. The same expression you can also simplify like this. You can also simplify like this. The same expression. Next. Okay. This expression, if you observe carefully, it contains V1 term, V1 dash term, V2 term and V2 dash term. Okay. This expression I write like this. Say H1 into V1 plus H2 into V1 dash plus H3 into V2 plus H4 into V2 dash. Understand? Plus H4 into V2 dash. Okay. What are here? H1, H2, H3 and H4. They are the Hermite shape functions. They are the Hermite shape functions. How they appear? That we see here. The Hermite shape functions will appear like this. I explain. Now, 1 by 4 into 2 plus j into 1 minus j whole square. This is the first Hermite shape function. H1. This is H1. Understand? Next. 1 by 4 into 1 plus j into 1 minus j whole square. This is the shape function H2. Next. 1 by 4 into 2 minus j into 1 plus j whole square. This is the shape function H3. 1 by 4 into j minus 1 into 1 plus j whole square. This is the shape function H4. Where H1, H2, H3 and H4 are the Hermite shape functions. Very, very important. Very, very important. Okay. Here the shape functions are derived in terms of the natural coordinate j. Okay. So what is the expression for representing the beam deflection? The expression for the beam deflection, V equals to H1 V1 plus H2 V1 dash plus H3 V2 plus H4 V2 dash. What is V1? V1 is here. V1 is equal to dV by dx at x equal to x1. Remember, the first node is specified by the coordinate x1. Understand? V1 dash, not V1. V1 dash is dV by dx at x equal to x1. V1 dash is next. V2 dash. What is V2 dash here? V2 dash is dV by dx at x equal to x2. Second node is specified by the coordinate x2. Therefore, you get V2 dash like this. What V1 dash and V2 dash represent? The slopes of the beam element at nodes 1 and 2 respectively. V1 dash and V2 dash represent the slopes of the beam element at nodes 1 and 2 respectively. Now, if you observe the Hermite shape functions, how they appear? They appear as cubic polynomials. H1, if you expand, you get a cubic polynomial. H2, you get a cubic polynomial. H3, you get a cubic polynomial. H4, you get a cubic polynomial. Why they are obtained as cubic polynomials? Because if you observe the expression for the beam deflection, V equals to A plus Bj plus Cj square plus Dj cube. The expression for beam deflection is a cubic polynomial. Therefore, you get the shape functions with same order. Understand? Right. Now, we shall see how the Hermite shape functions will vary with respect to length of the beam element. Take the first Hermite shape function, H1. Put j equal to minus 1. Then you get 1. At same node, determine slope. You get 0. You get 0. At same node, determine slope, you get 0. H1 you have, right? Differentiate H1 with respect to j. Then you get H1 dash. H1 dash equals to d by dj of H1. Okay. Then put j equal to minus 1. Then you get H1 dash. How much? 0. Understand? D by dj of H1 at j equal to minus 1 is H1 dash, that you get 0. Slope is 0. Okay? Next at node 2. Again. At node 2. H1 dash. H1 dash at j equal to plus 1. If you determine d by dj of H1 at j equals to plus 1, you get again slope 0. And if you plot, you get, a curve like this. Now this is how H1 is varying with respect to j or with respect to length of the element. Next, H2. H2 at j equal to minus 1, that is at node 1, right? The value of H2 is unity. The value of H2 at j equal to minus 1 is 0. And slope of H2 at j equal to minus 1, if you determine H2 dash equals to d by dj of H2 at j equal to minus 1, if you determine, you get unity. Slope is unity. That means, if you draw a tangent to this curve at node 1, it makes 45 degrees with horizontal. That is what help to understand. Okay. Next, H2 at j equal to plus 1. If you determine, right, you get 0. And slope is also 0. H2 dash at j equal to plus 1 equals to 0. Right? Therefore, you get a line like this. You get a curve like this. Next, H3 at j equal to minus 1. It is 0. And H3 dash at j equal to minus 1 is also 0. That is, slope is 0. Next, H3 at j equal to plus 1 is unity. And H3 dash at j equal to plus 1 is 0. Therefore, slope is 0. If you draw a tangent to this curve at this point, it becomes horizontal. And see how H3 is varying with respect to length of the beam. Next, H4. At j equal to minus 1, H4 is 0. And slope, here slope is unity, not 0. Slope is unity, it is not 0. Right? Because if you draw a tangent, it makes 45 degrees clockwise, hence you get minus 1 slope. It is minus 1, not plus 1. Make correction. Right? But H4 at j equal to minus 1 is 0. H4 dash at j equal to minus 1 is minus 1. Because if you draw a tangent, it makes 45 degrees at node 1. Next, H4 at j equal to plus 1, it is 0. And coming to slope, H4 dash at j equal to plus 1, it is 0. It is 0. Understand carefully. Therefore, slope is 0 here. Slope is 0. At j equal to plus 1, slope is 0. Right? And at j equal to plus 1, H4 is 0. Therefore, you get a plot like this. Okay? So far, what we have done, and we have discussed about the finite element modeling. We have seen the degrees of freedom at each node, what type of element we take, two-noded beam element we take for finite element modeling of one-dimensional beams. At each node, 2 degrees of freedom will take place. Right? What they represent? Beam, deflection and slope. We derived the Hermite shape functions in terms of the natural coordinate J. How many shape functions we get? 4 shape functions. They are the cubic polynomials. Right? They are designated by H1, H2, H3 and H4. We have also seen the variation of each shape function with respect to the length of the element. Thank you. Thank you.